All right, welcome back. We are here in chapter 2 of our Chemistry 202 material. We are in our chapter on coordination chemistry. In our previous video, we looked at transition metals in general. Here we're going to shift forward into coordination chemistry, a new class of compounds, looking at some details here, some terminology, some nomenclature, some of the properties of these compounds. In our subsequent video, look forward to that, we'll be getting into crystal field theory. But here, let's jump into our coordination chemistry material. As it turns out, the metals that we have in the world, they're not always going to exist as pure metals. They're not always going to exist as parts of our ionic compounds. They can also exist in the form of coordination compounds. This is a new class of compounds that have, well, a wide array of properties that might be interesting or useful for a variety of applications. In fact, a lot of these compounds show up in biology, utilizing metals as part of functional biological molecules, or they could be useful in manufacturing or catalysis, taking advantage of these metallic properties as they form these coordination compounds. In our course, as we said, we will look at the terminology and nomenclature associated with these types of compounds. We'll start to look at the various structures that might be formed, including a number of types of isomers. And in subsequent videos, we'll look into crystal field theory, a nice theory to examine color, bond energies, magnetism, and more using ideas from quantum mechanics. All right, so what are these coordination compounds? Well, metals, as we know, like to form cations, and when we have a cation, it will attract some electron-rich species. In the past, we've seen cations form ionic compounds with anions, but as it turns out, we can also form what are called coordination complexes. This is a new type of bonding. Our metals, which will be positively charged cations, will act as Lewis acids, compounds that can accept a pair of electrons. Our incoming molecules will form a new bond, and they will act as Lewis bases, donating a pair of electrons. We can see that in our image down at the bottom. Cobalt 3+ is positively charged. It is looking for some electrons. Ammonia, if you draw out the Lewis structure for ammonia, you'll see it has a lone pair. That lone pair can be donated towards this cobalt 3+. We're not just going to send those electrons over, but we're going to use those electrons to form a new bond. And the result here is one of these bonds that we see maybe on our image on the right. We have a complete chemical bond between that cobalt and our ammonia, where both of the electrons within that bond came from our original ammonia molecule. You'll notice the image on the right, we have this happening 6 times, but that is the idea. We have a pair of electrons coming from this other molecule, attaching themselves, forming a bond with our metal center. All right, to understand these compounds, we'll need to introduce some terminology, so let's go to it. We can define a coordinate covalent bond as what we were just talking about. When we have our metal atom in the center, acting as that Lewis acid, accepting a pair of electrons to form that bond. This is a covalent bond where both electrons come from just one of our incoming species. We call this a ligand. The ion or molecule that donates the pair of electrons is our ligand. So we have our metal, and it is surrounded by ligands. Our metal, we said, is a Lewis acid, something that accepts a pair of electrons. Those ligands are going to be Lewis bases, ions or molecules that donate a pair of electrons. when we have this Lewis acid base chemistry, we get to form new chemical bonds, again, where both those electrons in that bond come from our Lewis base, from our ligand. Within our coordination compounds, we can define the oxidation state of our metal. We've seen this in previous chemistry courses. This is the theoretical charge, pretending that all bonds have our electrons shared equally. This is going to be the same as the charge on our metal. For these compounds, we can also have the coordination number as the number of atoms attached to our central metal, right? Not just the number of ligands that are attached, but the number of atoms that are attached from our ligands. Let's be careful here. We'll see this in just a moment. Some of our ligands can attach more than once. Let's go back to our picture. We can see here is our central metal. It's this cobalt 3+. It is surrounded by, in this case, 6 ligands. 6 ammonia molecules have acted as Lewis bases and attached themselves to our Lewis acid, the cobalt. We call this our complex ion. Our metal and our ligands are a complex. This complex is covalently bound together. We have full chemical bonds attaching those ligands to our metal. They're a little bit different than some of the chemical bonds we've seen in the past because of where the electrons came from, but they are full chemical bonds. For this complex ion, notice here, we have a cobalt with a 3+ charge, and we have 6 ammonias, which are neutral molecules, and they've combined together to form a complex. Well, as a unit, they still have an overall charge of 3+. If our metal and ligand combination, that complex, has a charge, we're going to need some ions to counteract that charge. We can build some ionic compound using counter ions, and now our complex ion. When we're writing down our chemical formulas, our complex ion, we'll write that in brackets. Those brackets mean this is a complex. This metal and these ligands are covalently bonded together. Outside those brackets, we can have our counter ions. These counter ions are going to be attached based on electrostatic charges. We are essentially forming ionic compounds between our complex ion and whatever is outside our brackets. Notably here, our counter ions, they're part of our compound, part of this ionic compound, which will remain intact as a solid, but dissolved in water. Well, in water, ionic compounds tend to break apart into their constituent ions. In this case, we will have our complex broken apart from the counter ions when it's dissolved. We'd like to be able to determine the oxidation state of our metal. We'd also like to be able to determine the coordination number for our complex. Let's start with the oxidation state. Our oxidation state is the theoretical charge on our metal. So what we can do is look at each individual piece of this coordination compound and know that the individual oxidation states or individual charges need to add up to the overall charge on whatever species we have. All right, that's a long way of saying if we have a compound, the overall charge of this compound is written to the top right. In this case, well, we have something that is neutral. That means all the charges of the pieces of this compound need to add up to an overall charge of 0, neutral. We have a chromium. We have 4 ammonias. We have 2 chlorides that are part of our complex, and we have 1 chloride that is outside the brackets that is there to balance charges. Well, if we add up the charges of that chromium, those 4 ammonias, and these overall 3 chlorides, all those individual charges must add up to the total charge, which is 0. Let's write this out. We have chromium. We don't know the charge of our chromium yet. We have ammonia. And in fact, we have 4 of these ammonias. And we have chloride. Well, in fact, we have 3 total of these chlorides. If you add up these individual oxidation states, it needs to add up to the overall charge on our compound, which, since it's not written, has to be just 0. Some of these values we know. The ammonia is a neutral molecule. It has an oxidation state of 0. And, well, there are 4 of them, but 4 times 0 is still 0. Chloride, Cl. Well, Cl has a charge of -1, has an oxidation state of -1. So we have -1 for our chloride, and 3 total of those -1 charges. This is combined with our chromium, which we don't know what the charge is. I'm going to put it as X. But the charge on that chromium plus our 4 neutral ammonias plus our 3 -1 charged chlorides add up to a total of 0. This is a math problem that we can solve. The charge on our chromium has to be 3+. Or in other words, the oxidation state for our chromium is +3. Next, we can try to determine our coordination numbers. Coordination number is how many atoms are bonded to our central metal. We need to be careful. Some of our ligands have multiple bonds that can form from them. We're doing Lewis acid-base chemistry, where our ligands have some lone pairs that can donate towards our metal. Some ligands might have multiple lone pairs. We can see, well, one lone pair that can be donated from our ligand is known as monodentate. Dentate from the Latin for teeth. This can bite onto our metal with one attachment, one tooth digging into our metal. If our ligand has 2 lone pairs, where the geometry allows both of those lone pairs to point at our metal, we can call this bidentate. We can have 2 teeth biting into our metal from just a single ligand. Right? We need multiple lone pairs, which can be oriented at our central metal. We don't have to stop at 2. We could have polydentate ligands. Sometimes we have 3 or 4 or 5 or 6 lone pairs from a single ligand, all attaching to our central metal. Some more terminology here. When we have polydentate ligands, we call that a chelate, or the ligand itself is a chelating agent. We can look at some examples. All of these ligands have lone pairs that can bond to our central metal. Let's highlight. Here's our ammonia. We saw that before. Ammonia has this lone pair that can be donated to a metal. Water also has a lone pair that can be donated to a metal. It has another lone pair, but the geometry doesn't quite work out for this to be bidentate. Only one of those lone pairs can point at our metal. The other is pointing 109.5 degrees away, not helpful for forming 2 bonds, but we can certainly form 1 bond. Same idea for our halogens. We can have a lone pair bond to the central metal. Here this is oxalate. We can have, two lone pairs bond to the same central metal. Imagine there's a metal here. We can have both those pairs of electrons bind to the same metal. Bidentate, two teeth biting onto that one metal. Notice here, we need the lone pairs. We also need an appropriate geometry to do this. This ligand we call ethylene diamine. Again, we have two lone pairs that are spread out enough, and these single bonds are floppy enough for us to rotate around and bite onto our metal twice. On the right, we have what's known as EDTA. 1, 2, 3, 4, 5, and 6. This is a hexadentate ligand. 6 lone pairs that have the ability to wrap around and bite onto our metal, form that Lewis acid base chemistry with our central metal. We can see that this is that same molecule, hexadentate. We have enough flexible single bonds to curl up and wrap around our central metal. We can form a stable octahedral geometry around our central metal using those 6 lone pairs. EDTA, this is one of the best chelating agents. It forms these complexes very readily because it has the ability to do those 6 bonds. We will see a number of ligands in our course. Look for this handout on Canvas and in person. We'll get some good practice using these ligands in our coordination compounds. All right, for practice, let's see for these 3 compounds. Can we identify the oxidation state on our metal? Can we figure out the coordination number for these complexes? It will be helpful to use our handout, so feel free to pull that up. But let's see if we can do it. Let's walk through the first one together. We have a platinum. We have 2 chlorine ligands. We have 4 ammonia ligands. And we have 2 of these bromide ions as counter ions. For the oxidation state, if we add up all the charges on these individual things, they need to add up to the overall charge on this compound, which would be written to the top right if it was not 0. Since it's not written, the overall charge is 0. We know the charge on our chlorides have to be -1. We know the charge on our ammonias have to be 0. And we know the charge on our bromides also have to be -1. When we add all of these things together, we get a total of 0. Therefore, our platinum has to have an oxidation state of 4+. For the coordination number, we can look at what is inside of our brackets. We have 2 chlorides and we have 4 ammonias. Those are the ones that are attached to our platinum. We can draw our picture, right? We have platinum, we have 2 chlorides, and we have 4 ammonias. Outside of those brackets, we have some bromides, which are just there to balance out the charge. How many things are attached to our central metal? How many atoms are attached to our central metal? 1, 2, 3, 4, 5, 6. So our coordination number has to be 6. Again, to help us out, it's nice to know about certain ligands. What is the charge of these various ligands? What is the denticity of these ligands? That's on our handout. We can look that up, and maybe eventually we'll start to memorize some of these common ligands. But for now, feel free to utilize that information. All right, now that we have a grasp on the basics of our coordination compounds, we can start to look at maybe the three-dimensional structures. The geometries of our compounds will start to influence their properties. And what's nice, the geometries are dictated by the coordination number for these compounds. The three most common geometries we'll see are octahedral, tetrahedral, and square planar geometries. We mentioned our most common coordination geometries are octahedral, tetrahedral, and square planar. These are going to be determined by the coordination number. Anytime we have coordination number 6, our geometry will be octahedral. When we have coordination number 4, well, actually those are two options that we can have, tetrahedral or square planar. As a rule of thumb, if the electron configuration of the metal is whatever D8, then we expect to have a square planar compound. If we have electron configurations of D0 or D10, then we are much more likely to have tetrahedral complexes. There's more going on here, but this is at least a good rule of thumb to try to predict what geometry we expect. Lastly, we have one simpler geometry with a coordination number of only 2. We're forced into a linear geometry. You might be recognizing these shapes from Vesper theory, and those are still mostly true. With the small exception, square planar does show up in Vesper theory, but not in the same way. Here we have coordination number 4 and an electron configuration of D8. We'll have more about our geometry and the properties that result from them when we get into crystal field theory in our next video. But for now, let's move on to how to represent these various geometries. If we want to draw these compounds, well, we can decide how many atoms are attached to the central metal. We can check the electron configuration of our central metal in the case of coordination number 4. And lastly, we can try to account for any isomers that might show up. So as an example, chromium, Cl, H2O5, all in brackets. This is our complex, surrounded by 2 counter ions that are chlorides. We have a total of 6 things attached to our central metal, so we can try to draw this. Here is our metal in the middle. We have 6 things attached. That will be octahedral. We can use wedges to represent atoms coming forward or backwards, just like we've done in the past. One of these ligands is a chloride. The other 5 are waters. Notice here I'm drawing the atom that contains our lone pairs closest to the metal. Right, we have the lone pairs on our ligands forming the bond to that metal. It's good practice to show which atoms are attached to the metal by drawing them closest. H2O, OH2, both of these represent a water. Here we have 5 waters attached to our central metal, 1 chloride attached to our central metal, and we also have 2 other chlorides outside, present only to balance the charge. Since we have 2 chlorides, the charge on our complex has to be a net of 2+. We have a few practice problems here. Feel free to pause and see if we can draw these. A note for our second example, zinc has a D10 electron configuration, which we predict to be tetrahedral. All right, now that we can draw our molecules, it's time to get into the fun stuff. How do we name these molecules? We need to have a system of nomenclature that pairs a single chemical name with each chemical structure. For our coordination compounds, we have a lot of information that we need to convey. What is our metal? What are the ligands? What is the oxidation state on our metal? What are the counter ions maybe surrounding our complex? Right? A lot of information that we need to convey. Here are the rules. To name our compound, we would like to list our ligands alphabetically. We have our handout. We can see our list of those common ligands. Oftentimes for anions, we're changing the ending to O. For neutral ligands, maybe it's just the name of the molecule. For some of our ligands, we have some exceptions, some common ligand names. And when we have multiple of a ligand, we want to have a prefix to show how many of that ligand are present. For one, we'll just use the name. For two, we can do di. For three, we can use tri, tetra, penta, hexa. Occasionally, we'll have to change our prefix system to have our name flow off the tongue a little bit better so that we don't get confused. When we have ligands that also contain a prefix, or when we have ligand names that start with a vowel, we can switch to this other set of prefixes, bis, tris, tetrachus, etc. We'll try to take that as a case-by-case basis, and we'll get through some examples. Once we have our ligands listed in alphabetical order with the appropriate prefixes when necessary, we can write down the name of our metal. And our metal always has the oxidation state in parentheses after it, using that Roman numeral system. If we have a neutral complex or a cation complex, this is it. That's just the rule. Use the name of the metal followed by the charge. We get an exception when our complex, metal plus ligand, has a net negative charge. We need to change the name of the metal to 8 and occasionally switch to the Latin root for our metals when it makes the name sound nicer. Once again, we have a handout on Canvas to help us, but that's how we name our complex. The ligands in alphabetical order with our prefixes, followed by the metal with its charge, and occasionally changing the metal to the 8 ending if our entire complex is negatively charged. Once we name our complex, we can name the overall compound. If we have counter ions outside of the complex, well, we can name this just like we would any other ionic compound. The name of the cation, then the name of the anion. Either the cation or the anion might be this complex, and the other can just be whatever's surrounding it. I know this sounds like a mess. Let's go through some examples. Al, OH2, H2O4 plus. What do we have going on here? We have aluminum as our metal. We have 2 hydroxides as a ligand, and we have 4 waters as a ligand. We can try to picture this, right? We have aluminum surrounded by, looks like 6 things. 2 of these are hydroxides. The rest of them are waters. So we can try to at least visualize this. We'll list out our ligands alphabetically. We call water aqua. We call hydroxide hydroxo. And so alphabetically, we'll have this as tetra aqua, dihydroxo, aluminum, three. Some notes. Tetra aqua. We have two A's in a row. That's okay. We can call this tetra aqua, and that's fine. Two A's in a row can be allowed. Everything is just a single word. Tetra aqua dihydroxo aluminum, 3. Everything is lowercase. We do not need to change the ending for our metal because it is part of a positive complex. Because the charge on everything in brackets here is positive. So we'll leave the ending as aluminum instead of illuminate. We know the charge of aluminum is +3 based on, well, the math we've been doing previously. 2 negatively charged hydroxides, overall charge of +1. Let's do one more. For our second example, we have some sodiums. 3 sodiums, Na+, Na+, Na+. These are not part of our complex. They are outside. Inside, we have iron surrounded by 6 cyanides. Cyanide as a ligand we call cyano. And so we can call this hexacyano as the list of our ligands. This is surrounding our iron, but our complex here has to have a charge of -3 to counteract our 3 sodiums. Since we have a negatively charged complex, we need to have that 8 ending for our metal. We don't want to call this iron 8 because that does not sound well. So we can switch to the Latin root ferrate instead. Hexacyanoferrate, let's say Roman numeral 3 again, because the charge on that iron is 3+. Each of those cyano ligands is -1. +1 for each of these sodiums, -1 for each of these cyanides. Our iron has to be +3 in order to build that full neutral coordination compound. Hexacyanoferrate 3, that's the name of our complex. We have cations, we have anions forming kind of an ionic compound. So we can call this sodium hexacyanoferrate 3 as the name of this overall compound. Let's name the cations. Let's name the anions. For ionic compounds, we don't need any prefixes, just sodium hexacyanoferrate 3. If you're reading this name, you'll know that there are 3 sodiums in order to balance out our overall charges. We have one more problem here on the slide. Feel free to give it a go. We'll get many more opportunities to practice on our homework and in class, but those are the rules, and it does get easier with practice. Now that we have the basic naming rules down, we can look into some isomers. We've seen isomers for organic compounds. We can also have isomers for our coordination compounds. In general, our isomers have the same chemical formulas, but they are different molecules. They'll have different structures and different properties. For our coordination compounds, we'll have a few different ways of doing this. We can have different types of connectivities. We can have different orientations in space. And in fact, we can have a few different ways of doing each. We can start with what are known as coordination isomers. When we have ligands that are anions and counterions that are anions, we can have them swap places. If you have a bromide as a counterion, or a bromide as a ligand, and a chloride as a counterion, these two compounds will be different. Luckily, the naming rules we've already discussed can distinguish between these two, and so no new naming rules for these, but we do want to recognize that maybe this could occur if you have negative counterions as well as negative ligands. We can also identify what are known as linkage isomers. Some ligands are able to bond to our metal from one of two different atoms. Some of our ligands have multiple lone pairs available, each of which could act as the one that bonds to our central metal. To distinguish between these two with our naming rules, we can name our ligand based on what is bonded to the metal. We can have a different name or a different prefix or suffix to differentiate between what atom is attached within our ligand. Here's an example. If we have nitrite as a ligand, this is a nitrogen atom with two oxygen atoms, overall charge of -1. There is a lone pair on that nitrogen. There's also a lone pair on that oxygen. Either one could act as the atom that bonds to our metal, could act as that Lewis base, and will have different properties depending on which is actually bonded. When the nitrogen is bound to our metal, we call this a nitroligand. When the oxygen is bound to our metal, we can name this nitrito instead. We have another naming system when we have cyanato instead of isocyanato, depending on which atom is bonded. Either the oxygen or the nitrogen in this ion could be the Lewis base. Or for cyanide, the carbon or the nitrogen, cyanoligand as opposed to isocyanoligand, and so on and so forth. We'll just give a different name for the ligand depending on which atom is attached. When writing the chemical formula, we can write our bonding atom first in the chemical formula. NO2 would refer to the nitrogen attached to our metal. If you have ONO written out instead, this would imply the oxygen is bonded. We have that nitrito ligand instead of the nitro ligand. We've been looking at these molecules in our last couple examples. Let's take a moment, pause, see if you can give the correct name for each of these isomers. All right, we can also have geometric isomers for our compounds. This is when we have the same atoms connected, but we have a different arrangement in space. For square planar molecules, we can have cis and trans versions, just like we saw in organic chemistry across double bonds. Cis isomers will have similar atoms on the same side, close to each other, here 90 degrees apart in our square planar geometry. Trans isomers will have similar atoms far apart, 180 degrees apart in our square planar geometry. We can also have cis and trans isomers in octahedral complexes. when we have 4 of one ligand and 2 of another. Notably, our cis and trans isomers do have wildly different properties. This molecule written here has a common name, cisplatin. This is a cancer drug when it's in the cis form. When it's in the trans form, it is actually toxic and not going to be able to treat certain types of cancer. Another type of geometric isomer that shows up, we can have, well, face and meridian isomers when we have octahedral geometries with 3 of one ligand, 3 of a different ligand. The way we can identify these, we can try to connect the similar atoms together. Since this surface we draw does not go through the central metal, we consider this a face isomer, FAC. Alternatively, if we connect 3 of the same ligand and they do contact, that plane does contact our central metal, we call this a meridian, or MER. Just like the globe has meridians as things that bisect the globe, here our meridian, if we connect 3 of the same, this is going to cut our molecule in half and go straight through the central metal. All right, for practice here, can we pause? Can we draw all the geometric isomers for these compounds? Whether it's cis, trans, face, meridian, what might be possible? Our first example has octahedral geometries with 2 of one ligand, 4 of another. We can have both cis and trans versions of this. Our job, can we draw those? Our second example has octahedral geometries again, but 3 of one ligand, 3 of another ligand. This is going to be face and meridian isomers. Our last example, we have a bidentate ligand as well as 2 ammonias and 2 chlorides. Once again, I believe we can try to get cis versions and trans versions of this molecule. All right, and lastly, our last type of isomers that we'll investigate, we can once again have optical isomers. Optical isomers or stereoisomers, these are the same chemical formulas, the same connectivities, but when you take the mirror image of your molecule, it will be different from its corresponding mirror image. Just like our hands, left hand and right hand are different, but still mirror images, we can do that with some of our coordination compounds. For organic chemistry, we saw this with tetrahedral carbons with 4 unique groups. We could have that in coordination chemistry as well, right? If we have a tetrahedral coordination compound, which has 4 unique ligands. More common, however, are going to be these 2 other schemes, where we have 3 different bidentate ligands. 3 bidentate ligands attached to our central metal. For these bidentate ligands, you can almost think about it as a propeller or a fan. Right? Imagine a ceiling fan spinning around. If that fan spins clockwise, it will push air either up or down. Imagine you have a ceiling fan that spins clockwise and pushes air down. If you take the mirror image of that ceiling fan and also spin it clockwise, it will push air up instead of down. Right? The mirror image of a fan is going to be different. When we have 3 bidentate ligands, can draw this almost like these little wedges here. These 3 bidentate ligands in an octahedral geometry basically forms a fan structure. and each mirror image will be different from each other. We have two notation systems, S and R, L and D. We're not going to have identifying which is which as a focus of our course, but there are ways to do it. All right, we've made it through to the end of our second video here. We're looking at coordination chemistry. We've gone through the basics and the terminology. We've looked at our structures and our isomers and some nomenclature rules. Hang in there. We have one more video coming about crystal field theory. Going to start examining some of the properties and some theories behind these coordination compounds. But for right now, have a great day, and I'll see you in the next video. Thanks.